When describing transport mathematically, we could of course try to describe every single molecule, but that would be terribly complicated. So instead we divide into two different levels. What happens on the tiny level, on the molecular level, describing how molecules interact with each other, and what happens on a larger scale. On the larger scale, we talk about convection. Convection is when an entire package of air or liquid moves from one place to another. On the molecular level, however, we always have random movement, Brownian motion. So molecules move, they collide with each other and change direction. And if we have now blue molecules of a gas here and red molecules of another gas there, you see that they move around, and there's a barrier here, but if we take away that barrier, they will mix spontaneously because of this Brownian motion. And that's diffusion. We need to be able to calculate the convective transport and calculate the diffusive transport. Let's try first with convective transport. Here we have a pipe. Along that pipe we assume that we have some liquid moving, and we know the flux velocity, how many meters per second. Now try for yourself to write down what the mass transfer rate will be along the pipe and what the heat transfer will be along the pipe. So convective mass transfer and convective heat transfer. For mass transfer, I want you to try to write it in two different units, in kilograms per square meter and second and in moles per square meter and second. And we will use W divided by A for kilogram per square meter and second, and Na for mole per square meter and second. And for heat transfer, I would like you to express it as joule per square meter and second, and we will use the small q for that. And you have these other parameters you can use. So you have the area, you have the density, you have the heat capacity, you have the temperature, and you have the concentration. So pause here and try for yourself. Okay, did you manage? The mass transfer. Well, if you know the velocity and you know the density, you only need to multiply the two. The velocity, meter per second, times the density, kilogram per cubic meter, becomes automatically kilogram per square meters in second. So that is how many kilograms pour out at the other end. Okay, what about heat transfer along the pipe? Well, if you know the mass transfer, you know that heat transfer has to have something to do with that, right? So it should be something W divided by A times something. And what should we multiply it with? Well, we should multiply it with some kind of energy content. And we will talk about heat here as some kind of energy. And how much energy is in that? Well, you take the heat capacity times a temperature difference. And what kind of temperature difference? Well, you have to have a reference temperature. So this is a kind of enthalpy balance we make here. So you take W divided by A times heat capacity times the temperature difference. The temperature of the flow compared to a reference temperature. So what about mass transfer expressed as mole per square meter in second? Well, you can do that in different ways, but one way to do it is to take the velocity times the concentration. So meters per second times mole per cubic meter, that becomes mole per square meters in second. So that was convection. What about diffusion? Well, diffusion moves things from high concentration to low concentration. So the rate is some kind of constant times a difference or a gradient. And what Fick's first law states is that the molar transport equals a diffusivity times a concentration gradient. And we use J here for diffusive flux of A in the z-axis direction. And we take the derivative of concentration with respect to that direction, the z-axis direction. And there is a minus sign there. And that minus sign is because it moves from high concentration to low, not vice versa. So from high concentration to low, then you get a minus sign there. But what is the unit of diffusivity? Well, if you look at the other units here, mole per square meter per second, mole per cubic meter, and meter, that means that the diffusivity must have the unit square meter per second. But that sounds something like a painter, right? Trying to paint a wall and you paint the number of square meters per second. That sounds rather strange for something that is transported. But if you take the diffusivity and divide that with the distance, so square meter per second divided by meter, then you get meter per second, a velocity. So the diffusivity says something about how fast things are going if you know the distance. So to use diffusivities, you need to know something about that distance. Another way to express this is to use mass transfer coefficients. When you use mass transfer coefficients, you don't really care exactly what happens. You just measure things and say, okay, if I have this concentration here and that concentration there, how fast is things being transported? And then you determine your mass transfer coefficient K. And you get an equation like this. But wait a minute, if you have an equation like that, and you have fixed first law, you can compare the diffusivity and the mass transfer coefficient. And maybe you here realize that perhaps the mass transfer coefficient is the diffusivity divided by the distance. Perhaps. We will come back to that later and show that that might be the case, but it might not be exactly the case. So this is the two-film theory that says this, but we will talk more about that later. Okay, but how do you get a value of diffusivity? Well, you could do it like this. You take a handbook of some kind and then you look it up. But how did they get to that number? Well, they made measurements. So they determined them by experiments with, for example, like an equipment like this. But another thing you can do is to estimate the diffusivity based on different physical characteristics. And we will do both in this course. We will do one compulsory task with determining diffusivity, and we will do a lot of calculations where we estimate the diffusivity from physical characteristics.